Hello, Dr. Noor Aziman. We are students from Group 5. Our project is about the subtopic of Lagrange multipliers. For our group members, we have the first one is me, Yap Sun Chim, metric number 278031, Hafiza Hairul Sham 281187, Noor Aina Maisara Muhammad Razi 280840, and Martin Chu Chong Hung 281189. As we know, Lagrange multiplier is used in multivariable calculus to find the maximum or minimum of a function subject to a constraint. Lambda is used when the Lagrange multiplier function applied. In Lagrange function, the limitations are expanded with the edge of the variable lambda. That's called Lagrange multipliers. Managerial economics has a lot of use of Lagrange multiplier, but however, this topic is poorly touched in school and poorly understood by the student.
Assalamualaikum, my name is Hafiza binti Hairosham with the metric numbers of 281187. One of the most powerful application of calculus is optimizing indeed if we given some function. How do we know that the function has a maximum, and how do we know what is going to have a minimum? So here we are going to optimizing a special types to find a maximum and minimum but with a constraints and restriction. For instance, we get a graph of a function from a figure 1, and however, we get a constraints from the figure 2. And if it states that it needs to be on the particular curve and have been asked what is the maximum and minimum of the function restrict to the curve, when we need to figure out the maximum and minimum of the function, which is the figure 1, and we have been given a constraint optimization to a specific constraint, which is figure 2. So we need to know that we need to use the method of Lagrange multiplier. So here are some examples for a constraint optimization problem. From the figure, we can see that someone is driving a car on a mountain road. So he wants to climb as high as possible to have a better view of the moon. But you don't want to go off the road and you cannot fly to the moon either. So we are aiming for a highest position while satisfying the constraint that the car must be on the road. First and foremost, this is an optimization problem. An optimization problem can be either maximizing or minimizing depending on how we formulated the problem. From the key concept, we move to the next part, which is objective. Have you ever wondered why we use the Lagrange multiplier to solve constraints optimization problem? Is it just a special technique or even a must technique? Since it is very easy to use, we learn it like a basic arithmetic by practicing it until we can do it. But have you ever wondered why we need it? Technique for dealing with multiple variables allow us to solve more various optimization problem for which we need to deal with additional condition or constraints. There got two objectives in learning a Lagrange multiplier. First of all, we use the method to solve optimization problem with one constraint or even two constraints. And also, with the Lagrange method, we can solve the problem which is have two or more variables.
Assalamualaikum warahmatullahi wabarakatuh. My name Noor Aina Maisara binti Muhammad Razi, matrix number 280840. Now I will talk about the methodology of the study. The Lagrange multiplier method employs a quantitative approach. In this study, we are using a secondary data, which is there is an existing data that we take from diverse materials and resources. For the example and problems about this study were accurate from the internet resources. Why we choose this data collection method is because it is simple, quick, and also save time. Constraints complicate business circumstances which can be accounted for in management economics utilizing the Lagrangian and constraint function. The Lagrangian function is a strategy that integrate the function being optimized with the constraint function into a single equation. Solving the Lagrange function allows to optimize the variable that want to improve, subject to a set of constraints that can modify. A constraint function represents a restriction on the behavior. The constraint depend variable reflects the restriction. For example, the quantity of units that must be produced to fulfill a contract and the customer's budget. The difficulty of determining the greatest and lowest value of a function called an objective function. This is kind of case applies to the problem of finding extreme value of fxyz subject to the constraint gxyz equal to k. In solving the problems, there are a few methods applied. Firstly, of course, the Lagrange Multiplier method. Second is the Cope-Douglas production method, which a production function with two or more variables. Typical input include is labor and capital. It is similarity to describe utility maximization through the following function. The next is critical point. It is defined as those points which satisfy the constraint and where gradient f is parallel to gradient g. Last but not least, partial derivative. We illustrate how a particular variant of their models follows certain economic assumption. The path at which production change in relation to the quantity of labor is represented by the partial derivative.
Hi, today I want to discuss about the problem statement and the solution. Suppose your company has a negative contract that requires it to produce 1,000 units per day. The companies usually use labor and capitals to produce the goods. The amount of labors employed by the company, whereas L is measured in hours, and the wages measures with $10 per hour. Then the amount of capitals employed, where K is measured in machine hours and the price is $14 per machine hours. Therefore, your company total cost function is given by DC is equal to the function F, LK is equal to 10L plus 14K, and let Q be the production function is given by Q is equal to the function Q, LK is equal to 20 times L power of 0.5 times K power of 0.5. Where will consist of the relationship between the amount of the labor L and capital K used, and the Q is the number of good products. Q must equal to 1,000 units according to the contracts. To minimize the cost of producing 1,000 units of the goods, we must find the amount of the labor L and capital K to utilize. First one, we create the method of the Lagrange multiplier. Recognize that the variables we are attending to optimize is the cost. More precisely, we are attending to minimize the total cost. As a result, our company total cost is DC is equal to the function LK and equal to the 10L plus 40K. Our constraint is that the production function must create 1,000 units of goods. So our constraint is that Q is equal to the function G, LK is equal to the 20L power of 0.5, K power of 0.5, and 1,000 units of goods. 20L power of 0.5 times K power of 0.5 is equal to 1,000. So we want to put the left side to the right side. So we get the answer is 1,000 minus 20L power of 0.5 times K power of 0.5 is equal to 0. For method of Lagrange multiplier, it will become df LK lambda is equal to 10L plus 14K plus lambda times 1,000 minus 20L power of 0.5 times K power of 0.5. Let us test partial derivative of the method of Lagrange multiplier regarding labor and capital, where L and K are equal to 0. This equation implies that the goal function is evaluated. This means the total cost is minimized. For the differential, L is equal to 10 plus 0.5 lambda multiply negative 20 L power of 0.5 minus 1 times K power of 0.5. So differential L is equal to 0 for the critical point. So with the equation is 10 minus 10 lambda K power of 0.5 over L power of 0.5 is equal to 0. For the second one, we have partial derivative of the differential. K is equal to the 14 plus 0.5 lambda times negative 20 L power of 0.5 times K power of 0.5 minus 1. For the differential, K is equal to 0 for the critical point. So with the answer equation is 14 minus 10 lambda L power of 0.5 over K power of 0.5 is equal to 0. Let we also take partial derivative of the method of lambda multiplier regarding L's and set it equal to 0. This partial derivative also verify that the daily constraint of 1000 unit of goods is fulfilled. So differential lambda is equal to the 1000 minus 20 L power of 0.5 times K power of 0.5. So the differential lambda is equal to 0 for the critical point. The answer equation is 1000 minus 20 L power of 0.5 times K power of 0.5 is equal to 0. To minimize the overall cost of producing 1000 units of goods, we start to solve the three partial derivatives for the variable L, variable capital K, and the variable lambda simultaneously. Let us to solve for lambda by writing the partial derivative of E regarding L and K. For the equation 1, we have the 10 minus 10 lambda K power of 0.5 over L power of 0.5 is equal to 0. So we want to find the equation of the lambda in terms of L and the K. So lambda is equal to L power of 0.5 over K power of 0.5. For the equation 2 is 14 minus 10 lambda L power of 0.5 over K power of 0.5 is equal to 0. We also want to find the lambda in terms of the K and the level. So the equation is the lambda is equal to the 4K over power of 0.5 over L power of 0.5. By substituting equation 1 and equation 2 in the partial derivative of differential with respect to K for lambda in the previous equation. So we have the L power of 0.5 over K power of 0.5 is equal to 4K power of 0.5 over L power of 0.5. So we get the 1 level is equal to the 4 capital. In the constraint replace L with 4K. The partial derivative of L with respect to the L when the equation is 1000 minus 20 L power of 0.5, K power of 0.5 is equal to 0 when the L is equal to the 4K. So we change the negative 20 L power of 0.5, K power of 0.5 to the right side. So and change the L to 4K. So we have the equation is 1000 is equal to the 20 times 4K whole bracket holding power of 0.5 times K power of 0.5. So we get the K is 25. As a result, our company will require 25 machining hours of capital per day. When the K is equal to 25, we substitute into the L is equal to the 4K. So L is equal to 100. As a result, our company will require 100 of labor per hours. Finally, we can substitute terms and solve for lambda when the amount of the labor is L is equal to 100 and the amount of the capital K is equal to 25. So from the equation, lambda is equal to the L power of 0.5 over K power of 0.5. So change for the L is equal to 100 and K is equal to the 25. So we have lambda is equal to 100 power of 0.5 over 25 power of 0.5. So we get the lambda is equal to the 2. In conclusion, The cost of the producing 100 units of the goods per day is minimized by combining 100 hours of labor and 25 machine hours of capital when the lambda is equal to the 2.
For the second problem, golf ball producer Pro T has established a profit model based on the X number of golf balls sold per month measured in thousands and Y per month on the number of hours for advertising. According to the function Z equal to fxy equals to 48x plus 96y minus x squared minus 9y squared minus 2xy, where Z is measured in thousands of dollars. The budgetary constraint function that relates the cost of thousands of golf balls to the cost of advertising units is given by 20x plus 4y equal to 216. Now we have to find the value of x and y that maximize profit and find the maximum profit. To solve this question, first we have to create method of Lagrange multipliers, where we have the optimization function which is z equals to fxy equal to 48x plus 96y minus x squared minus 9y squared minus 2xy. To find the constraint function, we remove 216 from both sides of the constraint and divide both sides by 4, and we get 5x plus y minus 54 equals 0. The constraint function is equal to the left hand side, so we obtain the function gxy equal to 5x plus y minus 54. Let us compute the gradient of both fxy and gxy with the partial derivative. We can get that differentiate of fxy equal to bracket 40x minus 2x minus 2y times I plus bracket 96 minus 2x minus 18y times j. Differentiate of gxy equal to 5i plus j, where I is the partial derivative function of variable x and j is the partial derivative function of variable y. Now compute the equation of differentiate fxy equal to lambda differentiate gxy and change it into bracket 48 minus 2x minus 2y times I plus bracket 96 minus 2x minus 18y times j equal to lambda bracket 5i plus j. Let's set the coefficient of I and j to the same value, where coefficient I equal to 48 minus 2x minus 2y equal to 5 lambda I. Coefficient j equals to 96 minus 2x minus 18y equal to lambda. Equation gxy equal to 0 turn into 5x plus y minus 54 equal to 0. And we can get the equation system that we need to solve are equation 1 48 minus 2x minus 2y equal to 5 lambda, equation 2 96 minus 2x minus 18y equal to lambda, and equation 3 5x plus y minus 54 equal to 0. Now let us replace lambda first from equation 2, which is 96 minus 2x minus 18y equal to lambda, into the equation 1. After that, we expand the equation and simplify it, and we can get x equal to 54 minus 11y. Then we replace the answers x equal to 54 minus 11y into equation 3 and expand the equation. We get the answers y equal to 4. We sub the y equal to 4 into the equation x equal to 54 minus 11y, then we can get x is equal to 10. Then we know that tan 4 is the maximum value of the function fxy. We exchange it into the function fxy. We get the answers at tan 4 equal to 540. The conclusion that monthly production levels of 10,000 golf balls, and 4 hours of the advertising purchases, the maximum profit that can be achieved subject to the budgetary limit is $540,000.
So, for the conclusion, Lagrange multiplier are useful in our life, which is measured in economic. Based on our study for the first economic problem, we get the solution, which is to minimize the cost of produce. For the second problem of economic, also, we will get the maximum profit that can be achieved subject to the budgetary limits. It is able to increase the performance rate of a company. If we use the Lagrange multiplier method, it is able to increase the performance rate of a company and reduce waste of money, time, and also the energy can be used as much as possible. That's all from our group. Thank you.